Good lecture too. So thanks for coming back. So yesterday we kind of gave an overview of this, what modularity means, but without being very precise about things. And so the goal for today is to just kind of go over some of the things that I mentioned yesterday and try to make them more precise. And the particular thing that I want to focus on is how to go from a modular form to a Galois representation. So there was this step where you start out with a modular form F, so this holomorphic function on the upper half plane with lots of symmetries, and you associate to it this number theoretic object, which is the Galois representation. Two-dimensional representation of the absolute Galois group of, right? We had F going to row F. And so I want to try and make things more precise today. You want this F depends on some prime P, or maybe call this L. And the way that I want to do it is first kind of talk very generally about, why are we looking at the upper half plane, or like what's kind of the general framework in which we can expect to have something like a global Langlands correspondence, and talk about the very important averaging operators that are Hecke operators that are really key, because as it turns out, F is not just any modular form, but it's a special modular form that is a simultaneous eigenvector for these Hecke operators. And that's really the connection to representation theory, and I want to emphasize this. And then afterwards, we're going to state a version of this that's actually precise. And then we're going to start discussing how one might go about proving it. And I'm just going to start with discussing modular curves more precisely from a moduli theoretic perspective. So that kind of connection to algebraic geometry, or even arithmetic algebraic geometry. Okay, so that's the plan. And so the first thing is kind of general, but you don't have to worry. So you can either think generally if you're comfortable with that, or you can just take an example. And so I'm going to take G to be something called a connected reductive group. These are might also come up in Jessica Finson's colloquium later today, but you don't have to worry too much about it. So you can think of it as just like basically a group of matrices. So for example, you could take GLN, or even GL2, or SL2. Those are groups that showed up a lot yesterday. So GLN or SLN, or say a symplectic group. So matrices that preserve a particular form, like a symplectic form. But again, you could just take your favorite example, or you can think more generally. And then somehow the key is that when you start out with something like this, in order to talk about what modular forms might be, you have to talk about the space that they live on. And the space that they will live on is something called the symmetric space. So X will be the symmetric space for G of R. So your group is a group defined over Q. So you can think of it as matrices with entries in Q, but you can extend your scalars and look at matrices over the reals. So symmetric space for G of R. And this has a definition. Namely, my version of it is going to be, you look at the R points of the group and you quotient out by a maximal compact subgroup, and you also quotient out by some torus part. But okay, so this is like a bunch of symbols. You don't have to worry about it. I'll just tell you, for example, if you start out with GL2 over Q, or maybe let me even do SL2 over Q first. Then the associated thing is going to be SL2R quotiented out by, so the maximal compact subgroup inside SL2R is SO2R. So 2 by 2 orthogonal matrices with real coefficients. And the torus part actually doesn't come up, so we don't have to worry about it. That's going to be the X. So maybe I say XSL2. We'll call this X sub G. And as it turns out, this is the upper half plane, because, well, maybe I can leave it as an exercise, but just as a hint, so you have this action of SL2R on the upper half plane by Möbius transformations that we wrote down yesterday. So Z goes to AZ plus B over CZ plus D. So this ABCD yesterday was a matrix with integer coefficients, but there's not a particular reason to do that. You can expand and take real coefficients, and still, if you have a strictly positive imaginary part, you get a strictly positive imaginary part. So this acts on the upper half plane. And then to kind of identify the symmetric space of the upper half plane, you just have to show that SL2R acts transitively. And then you have to look at a special point, for example, the point I, so the square root of -1, and compute its stabilizer. And you can check that the stabilizer of I is the group of 2 by 2 orthogonal matrices under this action. And so this is how you get this identification. And so for us, we want to think about symmetric spaces, but in fact, we want to think about locally symmetric spaces. So in addition to doing this, we want to also consider certain quotients of these spaces by certain arithmetic groups. And so let's see. So SL2, if I start out with SL2, I get this. I actually generally prefer to do GL2. This is, you're going to see it's not that different. So X GL2 is just GL2R. Again, the same maximal compact, but now there's there's a non-trivial torus part that's like comes from the positive reals. You end up with a union of the upper half plane and the lower half plane. So we just remove the real line axis from the complex numbers, and you get this disjoint union upper and lower half plane. Let me give you one more example where I go to locally symmetric spaces. And this really has to do with, this might explain to you why somehow yesterday we saw that elliptic curves over imaginary quadratic fields took a lot more time to understand that they're modular than it took for rational elliptic curves. So if I take now SL2 over F, where F is an imaginary quadratic field. So for example, Q adjoined I. Then this X, so I can kind of really view this as a group over Q by taking something called Weil restriction of scalars. So it's a group over F, but we pretend it's over Q by kind of thinking of F as living over Q. And then the associated symmetric space ends up being, so I have SL2 of R, but tensor with our field. And if this is an imaginary quadratic field, so on one hand, you kind of adjoin all real numbers. On the other hand, you also adjoin something imaginary. This ends up being C. And then it turns out the maximal compact subgroup is the group of unitary matrices. So this ends up being SL2C, quotiented out by unitary matrices, 2 by 2 unitary matrices. And as an exercise, if you haven't seen this before, you can compute the dimension. The dimension ends up being 3. So I claim that this is, in some sense, let's say isometric too. It looks very much like hyperbolic 3 space. Something that you can check by hand is that the dimension is 3. So this is another example of a symmetric space. Another example where if you want to think about what modular forms would be, you have to take quotients of a space like this by certain discrete arithmetic groups. Okay, so you start out in this very general framework with some group of matrices. You look at this symmetric space, which is actually just a real manifold. So it doesn't necessarily have a complex structure. In some cases, it happens to have a complex structure, like when you have the upper half plane or the union of the upper and lower half planes. But in other cases, it has odd dimensions, so it doesn't have any chance of having a complex structure. And then you take quotients by arithmetic groups. But I want to do something slightly different, and I want to think about it more from a representation theoretic perspective. But either works fine. So for locally symmetric spaces, you can either take, so if you know what this is, then great. And if you don't know what this is, there will be another description. So I take a compact open subgroup inside G of the finite Adels. This is a restricted product. So with some funny topology of GQP over primes P. And I take this to be some compact open subgroup that's assumed sufficiently small. And then I start out with my xg, and I form xk like this. Take xg, cross this group, quotient it out by k on the right, and then this thing is quotiented out by g of q that acts diagonally. So g of q embeds into g of r, and g of r acts on the symmetric space. And then you quote, so it embeds in here, it also embeds in here. So GQP, right? G of q embeds into each GQP where P is prime. Okay, so this is like a very fancy way of thinking about this. Fact is that there are finitely many double cosets. So if I look at G of AS mod K on one side and mod G of Q on the other side, this is a finite set. And so then it turns out that you can rewrite xk as a disjoint union over I in some finite set of my original xg quotiented out by certain arithmetic groups in here. And typically these gamma i's, so for us, these gamma i's are really going to be cut out by congruence conditions from something like G of Z. So maybe our group has a model over Z, just like SL2, right? You can think about matrices that have integer entries and determinant 1. So SL2 has a model over Z, and then you can think about congruent subgroups. Subgroups cut out by congruence conditions. So in fact, a congruent subgroup. Okay, so examples. I come back to my first example over here. Right? This is 1. This is 2. This one is 3. And so example 1, you end up with gamma inside SL2Z, a congruent subgroup. And then our locally symmetric spaces end up looking like H mod gamma. Possibly, you could take some disjoint union of finitely many of them. It doesn't really matter. I guess in this case, it's not really going to be that, but in any case, it still doesn't matter. So you're only going to get one. Well, I guess it depends on what your group is, but in any case, so it looks like this. So like this kind of quotient that we talked about yesterday. And so the xk's like this, and they are these Riemann surfaces. Example 2 is essentially the same, because again, up to just looking at a connected component, it's still just going to look at like the upper half plane, quotient it out by an arithmetic group. So 2 is similar. And example 3 ends up looking more interesting because, so the xk's, the locally symmetric spaces, end up being things like this, where gamma I inside, so this is a congruent subgroup, and it's inside a group of 2 by 2 matrices, but no longer with coefficients in Z, but with coefficients in the ring of integers in our imaginary quadratic field F. So OF is the ring of integers. In F. So for example, if you started out with Q adjoint I, then it's C adjoint I. Okay, and these spaces, so they're quotients of hyperbolic 3 space by these discrete arithmetic congruent subgroups. And they're exactly the kinds of spaces that showed up in Mathilde's talk yesterday. If you remember, there was talk about hyperbolic 3 manifolds. So these are called arithmetic hyperbolic 3 manifolds. And another name for these particular spaces is Bianchi manifolds. Okay. And so these are the kinds of spaces on which modular forms and their generalizations live. And I'll make one comment about modularity of elliptic curves, and then I might not come back to it so soon. So if you start out with examples 1 or 2, so you're looking at SL2 or GL2 over Q, then the associated spaces have this complex structure, and that makes them closer to geometry, because we're gonna talk a lot about them. So these are called modular curves. We're gonna talk a lot about them the rest of the week. And that makes it easier to go from the modular curves on these groups from modular forms, from these highly symmetric functions on these spaces. It's easier to go to Galois representations if you have a space that has a complex structure and that's closer to kind of algebraic geometry. But on the other hand, in this case, these spaces don't have this complex structure, and they don't have the structure of algebraic varieties. They're really just real manifolds. Maybe they have, a metric, like the hyperbolic metric, but that's about it. So they have this very like analytic or topological nature. And so these are a lot harder to connect to geometry. So that's one reason why, it took a long time to go from modularity over Q to modularity over Q adjoint I. It's not the only reason, but it's somehow the one that I think is kind of easiest to appreciate if you haven't thought about these things before. Okay, so for the rest of the course, I really want to think about spaces that are close to geometry. And I'll just say that we're mostly going to think about modular curves. So the spaces, which for me, I always like doing GL2 better, because I think everything is cleaner. The moduli problems that you end up looking at are cleaner, but up to just looking at connected components, there's really no difference between GL2 and SL2. So I'm going to be thinking really about these examples up here. But I will mention that there's more general and higher dimensional spaces that do have this algebraic geometric structure that are called Shimura varieties, and they might come up in lecture 4. So at the very end, we might say something about those. But already there's a lot of interesting geometry that you can see in the case of modular curves. And so those are the spaces that we're going to focus on the most. Okay. So maybe this is a good breaking point if anyone has any questions. Oh, okay. So then what I want to do next is, so why did I introduce this perspective here, where I think about some level subgroup, but inside this kind of funny product of GQP with P ranging over all the prime numbers. I guess the reason that I did it, there's two reasons. One is that just as you saw in Mathilde's talk, you don't want to just think about one of these spaces. You really want to think about towers of these spaces. So it's important to consider the whole tower xk over varying k in order to access all the symmetries. So for example, right, I could have something where I have some congruence condition modulo p, but I can refine it by introducing a congruence condition modulo p squared, which leads to a smaller subgroup, which means you're quotienting out your space by less, which means you're getting a covering space. And so really what you have is a whole tower, and you see more symmetries by looking at the whole tower than you see by looking at just one single space. So somehow if you have the whole tower, in some sense you have an action of this really giant group on the tower. So you might go from one K to a different K, but you see this entire action. And this is what kind of the Hecke action is something that you go back to just one space xk, but it's an averaging operator that remembers the fact that you had the whole tower. So the next topic that I want to discuss is Hecke operators. So we talked about locally symmetric spaces. And I just want you to think about these locally symmetric spaces as the spaces on which automorphic forms live on. So modular forms generalize to automorphic forms. This automorphic means, well, it has to do with kind of having a lot of symmetries. These spaces are the spaces on which automorphic forms live on, but in order to really think about them from a more representation theoretic point of view, it's important to talk about Hecke operators. And again, that's one reason why I like seeing each individual GQP, because there's also a connection to the local representation theory that shows up in Charlotte's lecture course. So and here, so you can do things in complete generality if you like. So you can work with a connected reductive group of two, or you can specialize to your favorite example. And I'm going to specialize to my favorite example just to simplify and to make the notation very explicit. But what I'm telling you does generalize pretty much in the way in which I will describe it. So we're going to take our level to be, so there's going to be some piece that is away from P and some piece that is at P. And P is a chosen prime. And this part you can forget about. So I just want to focus on congruence conditions at my favorite prime number. And the way that I want to do it is first I'm going to assume that I'm somehow at a level that doesn't see this prime. So I'm going to assume that the group of matrices, let me write it here. So assume that KP is GL2ZP. And so if kind of you think about modular forms from a more classical perspective, this means that the level is prime to P. And this is the level at which you can define two Hecke operators. So you can define basically two Hecke correspondences. TP and SP on sort of R space XK. So for each prime number, if my level is as big as it can be, this is the maximal compact subgroup inside GL2QP, then I can define two Hecke operators. And really, this one is kind of boring. This one is interesting, so I'll focus on this one. So these are double coset operators. For, well, P001. So this is the one for TP, and P00P. This is the one for SP. This corresponds to TP. This corresponds to SP. And the idea is, again, that you really, what you want is to try to remember the fact that you have a GL2QP action on the whole tower. But because you want to kind of simplify things a bit, you want to work with just one level. And so the way that you remember this is via some Hecke correspondences or Hecke operators that know about elements in the group that are not in the maximal compact subgroup. And as it turns out, if you kind of think about double cosets, so GL2QP, things that are invariant under GL2ZP on both sides, these can be described in terms of these two Hecke operators. So I'm going to define a subgroup that is the so-called Iwahori subgroup. So I'm going to take K, I don't know, KP, sorry, let's say K sub P naught. I'm going to take this to be matrices inside the original K sub P, so inside GL2ZP, but that have an additional congruent subgroup, congruence condition. This is congruent to an upper triangular matrix, mod P. This is something called inside KP. This is called the Iwahori subgroup. And somehow the point is that if I take P001 and I conjugate KP by it, and then I intersect with KP, then what I get is the Iwahori subgroup. So this, if I want to understand how this 2x2 matrix will act on the tower at infinite level, but I want to try to remember some shadow of this action at finite level, K, where I have GL2ZP at P, then I don't have to go all the way to infinite level up the tower. I just have to go to this level, which is the Iwahori level. And then, so maybe K naught of P, I'll take this to just be the same level away from P, so I don't care what happens away from P, but I take the Iwahori subgroup at P. Okay, so this is the same level, but with an extra congruence condition at P. So that means it's going to be a bigger space. It's going to cover the original space. And so now we can write down a Hecke correspondence. So I have my original space over here, and I have this bigger space. So I've just taken a quotient by something smaller. So the space is bigger. And this is the natural forgetful mod. Okay, and I'm calling it P1. And then, so what I can do is I can conjugate this by P001. And if I do this, this becomes isomorphic to the space of level K upper naught P, where I have the same kind of congruence condition, But instead of upper triangular, I want it to be lower triangular, right? So you just have to kind of check what happens. So K thing. And this thing is so the same stuff, but gamma P has to be congruent to star 0 star star mod. Okay. And then, so this is at some other level that's still contained inside my original K. So it's still a smaller level, so it's still a covering space. So it still has a map, which is the forgetful map, to my original space. And so here, this is conjugation by P001. Okay. And I'm going to call this composition. If I go this way, I'm going to call this P2. And so this is what a correspondence is. I'm not going to really get a map from XK to itself, but what you want to get is this kind of hat, where there's one space that maps by some finite map, just a covering map, to my space, and then by a different covering map to the space. And then this is what the Hecke correspondence TP is. So this defines Hecke correspondence. Okay, and so explicitly, how do you play with this? Well, if I have a function here, I can pull back the function to the bigger space. And then I can kind of take a trace map down to the smaller space. And so that's what the Hecke operator on modular forms does. The Hecke operator TP, it will take a modular form here, it will pull it back, kind of view it as a modular form with fewer symmetries, but then take an average, this trace map, to go down to the original level, but the symmetries are sort of in a slightly different way. So it's kind of an interesting operation on the space of modular forms. And I could have just written down a formula on Q expansions, but I didn't want to do this because, so this is completely general, first of all, and second of all, it works on functions, but it also works on cohomology. It works on singular cohomology, if you know about that, or it works on de Rham cohomology, if you know about that. So like once you have this like very geometric relationship between these covering spaces, this translates to any kind of cohomology theory that you want to look at. And so that's why I like this perspective in terms of these correspondences and these covering maps. Okay, and I said there's another one, which is SP, and SP is boring. And the reason SP is boring is because, so this P00P, it's a diagonal matrix. So if I conjugate anything by it, it's not gonna, it's not gonna do anything. Everything commutes with P00P. So there's another, like, SP will really just be a map that acts on the space XK. You're not gonna have to go to a smaller level and really take an averaging map because it's a diagonal matrix. Right, so you can similarly, SP can be defined similarly, but in fact, it's more easier. So it's just XK equal to XK, that's P1, and then this map is an isomorphism to XK, and this is given by this conjugation. And that's all there is. Well, sorry, I didn't quite mean conjugation here. Sorry, I meant kind of multiplication by this. Sorry. This is multiplication by. Right, so what that means is you have your xg cross g of af modulo k modulo gqp, and I have an element in here that's a pair x comma g, And the G itself, you can write as a G away from P and a G at P. And then this multiplication would be, this gets sent to X, G away from P, G at P times P001. And then if you think about it just as a K coset, then you see that what this map is. So if you have a K naught P coset, it will go to a K upper naught P coset. So that would be in the case of TP. And in the case of SP, it's the same kind of thing, but you just multiply by P00. Okay. And somehow, I don't know, what makes these Hecke operators interesting is, in some sense, that your group is not commutative, right? So you're looking at 2 by 2 matrices, multiplication is not commutative, and so when you conjugate by a matrix, you do something interesting. If, say, we were working with a torus, so a group that is commutative, then the Hecke operators would be less interesting, maybe would be easier to understand. But already if you're looking at GL2, interesting things happen. Okay, so that's another topic that I wanted to kind of go in depth and try to explain what's going on. And the upshot will be that, so we want to think about these locally symmetric spaces that are spaces with lots of symmetries. We want to think about them in towers, and we want to think about Hecke operators acting on whatever kind of modular form that we have on this space. And so now I'm going to go back to modular forms. So I'm going to define M2 of, let's say, gamma 1n, or I don't know, I could do gamma naught n because I've already introduced what gamma naught is, and with complex coefficients, I'm going to define this to be the space of modular forms, or maybe for consistency of notation K naught, of weight 2 and level gamma naught P, gamma naught n, and over C. And so what does this mean? This means that, so we have F is a holomorphic function on our X K naught n. Oh, well, okay, holomorphic function on H plus minus, and I want that F of AZ plus B over CZ plus D. Oh, okay, maybe let's just say I don't want to write down this full definition right now. Maybe this is something that, because there's some translation involved in going between kind of this way of thinking about things and the way of thinking about the arithmetic group. And so maybe I don't want to do it right now, but it's something that you can go over maybe in one of the afternoons. And inside, so the point is that you have kind of functions that live in some sense at this level K naught of n. And there's a condition that, because these modular curves are non-compact, there's a condition that you have to be bounded as you go towards the cusps. So inside here, there is the space S2, K naught n C, which is the same thing, but cusp forms. Of level K naught n, weight 2 over C. But ultimately, I guess you have to think of them as some kinds of functions, or maybe because we're doing weight 2, as it turns out, these are really holomorphic differentials on these spaces. And then you can pull them back and push them forward. So pull them back and then take a trace, take this averaging operator. So on both of these spaces, you have Hecke actions. So if P is a prime that is prime to N, then you haven't imposed any congruence condition at P. Your level at P is GL2CP. And then you have TP and SP acting on these vector spaces, and TP and SP preserving the subspaces of cusp forms. And you can go even further and say that there's a whole action of a Hecke algebra. So I define this to be Z adjoin TP and SP. And this SP ends up being invertible because it's just given by that isomorphism. So adjoining this for every P that's prime to N. And so there's a whole big abstract algebra, and there's a lot of Hecke operators that act on these spaces of modular forms. So T acts on both of them, on N2, K naught N, C, and on S2. And one important thing is that for different primes, if I had P1 and P2, especially because you write it in this way where kind of you're separating P1 and P2 inside this Adelic perspective, this operation at one prime will commute with doing this operation at another prime. So these Hecke operators all commute. This is, you can take the kind of, right. This Hecke algebra is commutative and it acts on these spaces. And so we want to talk about Galois representations attached to modular forms, but to be completely precise, you have to only consider those modular forms that are simultaneous eigenvectors for all the Hecke operators. And so you have these vector spaces that are finite dimensional vector spaces over the complex numbers, and you have a lot of these averaging operators acting on these vector spaces. They commute. It turns out you need a bit more. They also have nice adjoint operators and they commute with their adjoints. And then you can show that you can diagonalize them. So you can find a basis consisting of eigenvectors. And that's what eigenforms are. So we go here. And by the way, this is all still general. So, I've written it for GL2, but it also works for higher dimensional Shimura varieties or for spaces that are not Shimura varieties. So one can show that, say, for instance, M2, gamma naught, K naught, and C, or S2, K naught, and C, admit bases for consisting of simultaneous eigenvectors. For the Hecke operators, PP and SP, where P runs just over all the primes, so infinitely many primes that have no factors in common with N. And so what we're going to look at from now on, from the perspective of Galois representations, is we're going to look at eigenvectors for all the Hecke operators in here. And so I'm going to kind of call such an eigenvector an eigenform. And I want to look at cusp forms because those are, in some sense, the modular forms that are really new for the group GL2. What you see in the kind of difference between M2 and S2 is the space of Eisenstein series, and that can be described in terms of automorphic forms for smaller groups, and in this case, the smaller group would be GL1, or maybe GL1 cross GL1. So kind of what happens at the cusps at these finitely many sets of points, you can understand differently, and the ones that are really new for GL2 are these cusp forms. So that's what we're going to look at. And maybe I want to state the theorem on going from these kinds of eigenforms, so cusp forms for the group GL2 over Q that are simultaneous eigenvectors of Hecke operators, so going from these to Galois representations. So this is a theorem that's due to Eichler, Shimura, and Helene. And proved more than 50 years ago. Let F in here be a normalized eigenform. So it's an eigenform, and normalized is really easy. So that just means that I can write my F of C. So it's a cusp form, so it starts from 1 to infinity, an q to the n. And then it's just when you have an eigenvector, you can rescale it. And we're going to normalize it so that a1, the coefficient of q, is 1. So it's just rescaled in this way. And then to these, we will associate Galois representations. So let Kf be the field that you get by starting with rational numbers and adjoining to this field the coefficients a1, a2, a3, and so on. The Fourier coefficients of our eigenform. So the first thing is that this is a number field. And that's something that's really surprising. And it's something that we don't, so in some slightly different settings, don't necessarily, we don't know how to show this in full generality. So this is the first kind of sense that you really have a connection to number theory. And I'll explain what the key is, but the first thing is that these Fourier coefficients end up, so if I take n to be a prime, little n to be a prime p, and I look at this normalized eigenform, then a sub p is not just a Fourier coefficient, it also ends up being the eigenvalue of the Hecke operator Tp. So this isn't just Fourier coefficients, it's really, you should think of them as giving you systems of Hecke eigenvalues. And so the first thing is saying that the Hecke eigenvalues of this modular form of weight 2 are algebraic numbers. And in fact, they all live in some finite extension of the rational numbers. And a priori, there's no particular reason this should happen, just by taking, some highly symmetric function on the upper half plane, or by taking some holomorphic differential on a Riemann surface. There's not a particular reason to get this algebraicity, but it turns out that you get it. And moreover, and one side comment is that in the special case where this modular form is really corresponding to an elliptic curve, you can see that because in that case, the field Kf is just Q. So the ones that come from modular forms, the field over which their Fourier coefficients are defined is really the field of rational numbers. And moreover, you can construct a Galois representation. And the way that you want to do it is you want to vary, say you want to construct one for each prime. And the way that we'll do it is say for every prime lambda dividing L of this number field. So this finite extension of Q, there exists a unique two-dimensional continuous, irreducible Galois representation. So Galois representation just means representation of the absolute Galois group. And this is going to be rho sub f lambda. And it's a representation of the absolute Galois group of Q. And it's two-dimensional. And it's valued, essentially you want it valued in QL, the L-adic completion of Q, except that because these coefficients aren't necessarily defined over the rational numbers, sometimes you need to go to a finite extension there. And the finite extension that you go there is the completion of the number field along this prime. But you don't have to worry too much about that. If you want, you can think about kind of the case of modular forms attached to elliptic curves, the case where KF is just Q, and the case where this is just QL. Okay, so there is something like this. And this is characterized in a specific way. So this is completely determined by what I'm going to tell you. For every prime P that doesn't divide N and that doesn't divide L, this representation, you can kind of view it as a representation of the local Galois group of just the field of p-adic numbers. So it's kind of the decomposition group at P. And then this is unramified, which means it's as simple as you can hope for. In fact, it's just given by one 2x2 matrix that's evaluated at this conjugacy class, which is the Frobenius. So determined by rho f lambda, evaluated at this conjugacy class, the Frobenius. And you can say what the characteristic polynomial of this one 2x2 matrix is. And given that all of this is really well defined only up to conjugacy, it's, getting the characteristic polynomial is really the most that you can hope for. So, and the characteristic polynomial of rho f lambda from P is x squared minus apx plus P. So the Fourier coefficient that shows up, the coefficient of Q to the P in the Fourier expansion of the normalized eigenform, which is also the Hecke eigenvalue of the Hecke operator TP, shows up as the trace of this matrix on the side of the Galois representation. Okay, any questions about the statement of this theorem? Maybe I want to say, what does it mean that it's characterized by? So if you had a representation of a finite group over a vector space of characteristic 0, so you could think about over C or over one of these L-adic fields, QL, then the representation would be determined by the traces of, by its traces. So you have a bunch of matrices, well defined up to conjugacy, and the collection of traces determines the representation. Kind of, remembering the character of the representation. Now, this isn't a finite group. This is a really big profinite group, very complicated, very hard to understand. But the Chebotarev density theorem is a result that tells you that these conjugacy classes of these Frobenius elements as you go over infinitely many primes that are just, ignoring this finite set here, these are dense. And so there's kind of two things. One is you can find a dense set of elements in here coming from the Frobenius elements. And the other is that the traces over there really pin down the representation. So this is by the theorem. And then there's a result. The fact that the representation is characterized by the traces is a result of Brouwer and Nesbitt. And so that means, right, it's not just that you match the eigenform with some Galois representation in some arbitrary way, it's that the Galois representation really, there's only one way in which it can look. Because it's really pinned down by the condition that the Fourier coefficient shows up as this trace. Okay, so that's one thing. As it turns out, you can go the other way as well. And if you know what the Galois representation looks like, and you can look at the traces at these Frobenius elements, then if that representation comes from a modular form, there's really only one modular form it can come from. This is a result that's known as strong multiplicity 1. And so the point is that this theorem really kind of connects the F and the rho F in a very, very tight way, right? And if you want, also as you vary lambda, so as lambda and L vary, these rho F lambdas satisfy certain compatibilities. So any one of them is enough to recover S. And also, if you have two of them, then maybe you have to exclude an L1 and an L2, but other than that, they have to match up. And then there's some more extra strong conditions on the Galois representations that are not needed to describe them uniquely, but that were conjectured to hold and then proved to hold as well. So there's like extra properties that they have that are sometimes useful. For instance, you can also describe what they look like at primes dividing n. You can also describe what they look like at L. You can also describe what they look like on complex conjugation, which is the only element of the absolute Galois group of Q that you can write down explicitly. We know that those are odd, so they have to essentially be conjugate to 1, 0, 0, minus 1. So there's other properties that they have. So these satisfy certain compatibilities, and then there's other properties at at L, N, and infinity that you can establish and that are useful when you try to kind of be more precise about the Langlands correspondence. Okay, so this is all I had for today. So what we're gonna do on Thursday is talk about some ideas that go into the proof of the theorem, so that you have a sense for how modular curves and their geometry are used to establish this kind of result and to get this connection. So thank you. Questions? Sorry, I forgot to do that. I'm sharing my.
A very random questions. For like those symmetric spaces, is it possible to consider like the field is not like complex of the real numbers, but for example QP or CP?
There are some local analogs of symmetric spaces that are p-adic symmetric spaces. But they don't show up as much when you try to think about the global Langlands correspondence, but they do show up in local Langlands. Yeah, so there's definitely, right, there's kind of, maybe you've encountered like the Drinfeld upper half plane, for example. That's kind of some p-adic analog of our H. Yeah.
Can you explain again how the Chebyshev density theorem factors into this statement?
Right, so I guess what I'm saying is that first, let's try to pretend that this was just a finite group. And then the Brouwer-Nesbit theorem would tell us that the representation would be determined by its traces. So like if you knew, okay, these are the traces, this is the trace at one element, this is the trace as another, right? That would characterize the representation. There couldn't be two that give you the same list of traces. And I guess what the Chebyshev density theorem allows you to do is allows you to apply this even in a setting where you have a very complicated profinite group here. Because you can't quite understand every element, but you can understand a dense set of elements, and that turns out to be enough.
Okay, thank you.
Sure. Yeah.
When you said strong multiplicity one, what is weak multiplicity one?
I always get confused about this, but so there's one question of, thinking about a modular form as kind of a vector inside a space of automorphic representation. There's this kind of, or like, there's the question of how do automorphic representations contribute to L2 and with what multiplicity they contribute to that. And I think that's the weak multiplicity one. And then the strong multiplicity would be the result that if you know the Hecke eigenvalues at all but finitely many primes, this determines the automorphic representation.